There we go. Let's talk about crash recovery, or durability. So durability in an in-memory system. Memory is not a reliable medium yet. So if you write a node to a skip list, it's not and you restart the machine, you're out of luck. That you can't assume that that's still going to be there. And even if there is, so we were talking about non-volatile RAM. There's always a hierarchy. So today, if you look at disk, which is durable, there is still a hierarchy. In Amazon, EBS is kind of the most premium storage that you can attach to a node. Actually, there's something even more premium than this, which is direct attached SSDs in Amazon now. There's S3, which is a little bit cheaper and a little bit slower. And there's Glacier, which is a lot cheaper and a lot slower. And users still want to take advantage of this hierarchy. So they'll still say, I want hotter data here, colder data here, and extremely cold data here. So even in the world of having non-volatile RAM, we as kind of database designers and database implementers can't ignore the fact that there is a storage hierarchy, and users do care about the storage hierarchy. Another note is to operate at in-memory speed. So to be able to write as fast as people expect with an in-memory database, your writes need to be sequential. And this is where that point about SSDs come in. SSDs have insanely fast sequential writes and insanely fast concurrent sequential writes. This is a big deal. So on a rotational disk, sequential writes are pretty fast, but concurrent sequential writes are not fast because there's only one needle. On an SSD, that's not the case, and concurrent sequential writes are also very fast. So the combination of those two make SSDs very, very, very fast and fast enough at sequential writes for an in-memory database to actually keep up with the sort of workload expectations that you have in the in-memory world. So how does this work? Oh, go ahead.
How do you leverage these concurrent sequential writes?
Well, you can write to an SSD with multiple threads and get, to a certain point, more performance, right? So that's, for us as kind of durability implementers, that's a very new thing. And it requires a little bit of re-architecture. Yeah. What's up?
In your opinion, how much slower were random writes on SSDs? And in your experience, did you happen to measure or?
I haven't really, I can't answer that number with like, oh, it's 10x or 100x slower. Yeah, it depends on a lot of things. And actually, SSDs are getting faster at random writes as well. But I would say that it is true that if you can boil things down to sequential writes, you set yourself up very well. So I'll give you another example why. Sequential writes mean that you get better batching over the network. And if you're using network-attached SSDs like EBS, you still benefit with sequential writes. Like sequential writes basically boil down to the computer science trade-off of batching. And if you can get something which is fundamentally random and sort of boil it down into a batch-based thing, then you'll get sort of better performance, or at least as good performance. That's a good question. Another reason it matters a little bit less is that non-volatile RAM is coming, and non-volatile RAM doesn't matter. Yeah. Okay, so durability in the row store. First thing is indexes are not materialized on disk. What's up?
Just want to think, like, what does it matter?
In the world of non-volatile RAM, random writes to SSDs matter less.
Okay.
Yeah. So durability in the row store. First thing is indexes are not materialized on disk. The reason is we never need to read indexes on disk because the working set of data for the row store is in memory. And so we don't need to write them to disk, and we can actually recover them on the fly. So that we don't care so much about the fact that it would use more disk space. We care about the fact that logging becomes very, very cheap. So we only need to log primary key data on disk in a row store. So for example, we don't partially manipulate a secondary index on disk and need to record the fact that we did so in a log, so that if that transaction commits, we need to undo that, right? The working set of data is in memory, and to reconstruct the system of record, state of the world kind of truth, you only need the schema of a table and primary key data, because you can populate indexes based on that information. Now to kind of optimize recovery performance, we take full database snapshots periodically. And I have a picture which kind of explains why that makes a difference. And the last thing is durability is tunable to be synchronous or asynchronous. There are some workloads where their data loss means something different. So most workloads, when you think about data loss, you're thinking about the worst case. So in the worst case, I want to make sure that I don't lose any data, which means that I'm willing to penalize the common case to a certain extent to be able to ensure that in the worst case, I lose no data. And for system of record, kind of bank or cash register type workloads, that trade-off makes a lot of sense. How many people here have heard of Internet of Things? It's a nice buzzword. Internet of Things workloads, where you're collecting a lot of data from a lot of sensors, there's a different kind of data loss. And that kind of data loss is, in the common case, am I actually able to collect enough data that I can make meaningful analytical sort of, or rather I can answer meaningful analytical questions on this data. The fidelity of an individual data point doesn't actually correlate with the correctness of their workload. It's how much data can they ingest and how quickly can they ingest in the common case. And in the rare event that a machine goes down, they're willing to accept the fact that they lost some percentage of their kind of randomly sampled data and move on from there. The other reason is that this data tends to be windowed in time. And so by 24 hours from now, or by 24 hours from when a machine fails, it just doesn't matter. And in those workloads, it actually is more correct to have asynchronous durability than synchronous durability from the user's perspective.
What's your default?
The default today is still asynchronous. No comments on whether or why that may change in the future. However, the kind of financial customers that are using MemSQL are actually running, for the most part, with synchronous durability, even in those Internet of Thing type use cases. So here's a picture of kind of snapshots and logs. Here's a log of some data. You can see we insert, delete, delete. If you kind of compress this log into a snapshot, it's just one insert. And so the value of replaying a snapshot over replaying a log is A, you can replay all records in the snapshot in parallel because they're all inserts. And B, you kind of remove things like this insert and delete, which at the end of this kind of point in time don't need to exist. And so these snapshots basically make recovery a lot faster, and the recovery of log 1 plus log 2 is equal to the recovery of snapshot 1 plus log 2. So you have exactly the same kind of end state once you recover either way. So how does durability in the column store work? And to Andy's point, it's actually very straightforward. So metadata is in a lock-free skip list. We use the ordinary sort of row store mechanism. Column store segments themselves are huge. They're several kilobytes or even megabytes. And they're read to and read from and written to sequentially. So what that means is we can synchronously write them to disk. And they're kind of past that threshold where whether you do it synchronously or asynchronously actually matters. So it's cheap in the kind of column store sense to always synchronously write these things to disk. And finally, the writes that need to be at sort of this memory speed are to the sidecar row store, which is just logged in the ordinary row store way. So the column store kind of, the only additional piece of durability in the column store is very simple. It's just, as we write column store segments, just synchronously write them to disk. What's up?
The reason it makes sense to always synchronously write those is because you're bound by the throughput to the disk rather than...
Exactly. Yeah, the sort of the latency throughput equation at that scale means that you don't kind of gain a latency benefit. Yeah.
Can different fragments of the same table be stored in row store and the column store?
Different fragments of the same table. Yeah, that's exactly the point of the row store column store thing.
Okay,
Yeah.
that's the common case.
Yeah. So the idea is that recently hot or recently written rows live in the row store part. In fact, the row store and column store parts, or more generally, each sorted run of the column store are mutually exclusive. So, yeah. And how does crash recovery work? You replay the latest snapshot and then every log file since. There's no partially written state on disk, so you don't need to do any undoing. And the column store just replays metadata. So it populates a cache of these columnar segments on the fly as you read them, but to kind of be available and online to serve queries, it merely needs to replay metadata. And replication is just continuous replay over the network. So replication just extends naturally from recovery. What's up?
So during the recovery, you recover multiple version data or just not recover a single version data?
Well, that is this, right? So we only need to recover a single version. Yeah. There's no partially written state on disk.
No, I think his question is refers to the multi-versioning aspect of things.
Yeah.
And I guess if you do recovery, you end up with different versions.
So log recovery is sequential and single-threaded, right? So the log recovery is the only recovery where you would have two elements of the same file that you're recovering that could overlap, and it turns out that it's sequential. So you can implement it with garbage collection, but you also know that no one else is going to touch that row concurrently with you, so you don't really need to.
I'm quite,
Yeah, so the log recovery, you mean the value logging recovery or?
Yeah.
So why the value logging recovery is sequential? Because well, I think the value logging recovery can be parallel, right?
Value logging recovery can be implemented in parallel, but it's insanely complicated. So the reason it's implemented sequentially is that you could have an insert and a delete, right, that touch the same row. And if you don't replay them, if you don't replay the insert and then the delete, you might not end up with the right state.
Okay.
Yeah. There are systems that do it. It turns out in MemSQL, because we actually store data in shards in the distributed system, we have mutually exclusive logs, and it turns out to be one mutually exclusive log per core. So there's not actually any real benefit the way that people run MemSQL to replay logs in parallel.
So do you snapshot the indexes? Or do you pursue the indexes?
No.
Okay. So every time you just reconstruct the index, right?
Yes, yeah, I said that explicitly a few times, yeah.
Okay, so
So you said you have one persistent log per core. Does that mean you have one instance of MemSQL per core?
No. So again, so we're not going to have too much time to talk about it, but the way that distributed MemSQL ends up getting set up is that it sets up shards, and there are multiple shards per process. So MemSQL is running one process per machine, each one with multiple shards, and each shard has its own snapshot and log. Yeah.
So you are processing and recovery in parallel.
You are,
You're
but
not
it's not in the
processing
same
one
log. Exactly. Yeah. So it's insanely complicated to replay one log in parallel.
Yeah.
It is insanely simple to replay multiple logs in parallel.
So they are doing silo harm.
Yeah.
Yeah.